Good morning to one and all. I am Parthiban, working as assistant professor in the Department of ECE, Sri Muthukumaran Institute of Technology, Mangadu, Chennai. Now I am going to talk about the subject called electron devices. The subject code is EC25C01, which is meant for regulation R2025. Now I am going to talk about the unit 4, which deals with FET. FET is nothing but the field effect transistor. Earlier we have seen about the BJT and its three modes of operation and its characteristics. So it is very much as if like BJT but with the difference. What are the similarities between the FETs and BJTs that we can have? Both can act as an amplifier, both can act as a switch, both can be used for impedance matching purposes. The difference between the FET and BJT lies, whereas the BJT is a current control device, FET is a voltage control device. FET is having a very high input impedance, whereas BJT is having a very less input impedance. FETs are less sensitive to temperature variations as well as in the radiation environment, whereas BJT is more sensitive to variations. FETs are generally more static sensitive rather than BJTs. FPDs occupies a very less space compared with BJT. So FPDs occupies a very less power also compared with BJT. So these are the major differences that we can have. Now we can see the FET construction. Generally if you say FET, it is nothing but the JFET only, which is called junction field effect transistor. There are two types of JFETs or FETs that are commonly called based on the channel that we are having. One is called N channel, another one is called P channel. But here also N channel is more popular and very widely used because as I already told you, the holes have less mobility compared with electrons. The electrons have higher mobility, that will be around 1.8 times faster than that of holes. So N channel type is more popular in FET. You see there are three terminals are there. One is called gate, the other one is called drain, the other one is called source. So you see two layers are there. So in and around P layer is there. In between that is N layer. It is typically resembling as if like a diode but with a difference. Since both ends are covered with the P layers, in diode it may not be. So it has been taken by means of the leads through ohmic contacts. So here the one good feature is that is the drain and source are always interchangeable. So there is no characteristic change will occur, but gate should be connected and maintained properly. Gate is nothing but the controller, or we can say a modulator. So by controlling gate bias, we can able to control the FET or JFET. So by varying the gate bias or gate voltage, we can able to vary the characteristics of FET. So FET is having a three terminal. Actually, it is a two-layer device only, but it is having a three terminal. The first terminal is called gate, the next terminal is called drain, the next terminal is called source. So by varying the depletion region, we can able to vary the characteristics. By applying the bias, we can able to vary the depletion region thickness. By varying the thickness, we can able to vary the characteristics. We can able to vary the voltage as well as the current. There are three basic operating conditions for JFET. One is when VGS is equal to 0, the VDS is increasing with respect to some positive value. In the next case, when VGS is less than 0, the VDS is at some positive value. The third one is that is called voltage controlled resistor, or it is also called voltage variable resistor mode. So these are the three modes of operations for a JFET. So the first case, when VGS is equal to 0, with the VDS increasing to the some positive value. What happens? You see, when VGS is equal to 0, VDS is increased from 0 to a more positive value. What happens in the depletion region is, that is between the P gate and the N channel, it increases as electrons from the N channel combine with the holes from the P gate. So increasing the depletion region decreases the size of the N channel, which increases the resistance of the N channel. Even though the N channel resistance is increasing, the drain current, that is ID, from source to drain through the n channel is increasing. This is because when VDS is also increasing. In the next case, we can see there is a pinch off condition. When VGS is equal to 0, VDS is further increased to more positive, then the depletion zone gets so large that is pinched off, or it's also we can say a finished state of N channel. So this suggests that the current in the N channel would drop to 0, but it does just opposite. As VDS increases, so also the ID also increases. So pinch off is nothing but the saturated condition in the FET. You see from the graph, so this graph depicts the characteristics of JFET. So in the x-axis we are having the VDS. VDS is nothing but the drain to source voltage. In the y-axis we are having the drain current. So you see the variation that is occurring. So you see for the N channel resistance how it is varying. Actually it attains the saturation level. So that point that is called VP is called pinch off point or pinch off voltage, which is also said. So which is demarcated there. So parallelly it is depicted as IDSS, which is nothing but the saturated condition drain current. So the pinch off point is marked. From there we cannot able to exert the control on JFET. That is what very important. That is depicted in the diagram as VP. So even if you increase further, there is no variation. So it attains the saturation value that is referred as IDSS. The ohmic value of the channel is maximum under this condition. So this is a clear representation of the characteristics of the JFET under saturated condition. These are the various references that I taken for the slides. So particularly the Milman-Akias as well as the Mehta as well as the Rider are the important books that I referred for taking the slides. Once again, I am thanking you one and all for hearing my lecture patiently. Thank you one and all.